a team shows up from Los Alamos to run some calculations, and the purpose of the calculations was kept secret from the operators. Herman Goldstein and Adele Goldstein worked with the Los Alamos team to translate the needs of their problem into a configuration. One of the operators in a memoir described Goldstein standing in the middle of the room like a conductor, reading out from this big piece of paper how all the switches and wires needed to be set, and them working around the room, setting the thing up appropriately. They took the results back to Los Alamos. It later became clear that this was part of a huge ongoing effort within Los Alamos to determine the workability of Edward Teller's design for a super bomb, the original attempt at building a hydrogen bomb.
Welcome to My Nuclear Life. I'm Shelly Lesher. Today on the podcast, I have Thomas Haigh, a professor of history at the University of Wisconsin-Milwaukee and author of 2 books, Eniac in Action, and next month, his new book will be released called A New History of Modern Computing, which he co-authored with Paul Ceruzzi of the Smithsonian National Air and Space Museum. Thomas's new book puts the story of computing into one place. If you have an interest in history or you want to know where your smartphone or PC started, you should really check out the new book. Our episode doesn't even cover the first chapter of this history, so there's a lot left for you to check out and learn. I want to make a couple of quick announcements. First, this episode was recorded in a temporary location, so you might hear some minor audio issues. I'm really sorry about that. Second, since August has an extra Tuesday and the end of the month is a chaotic time for anyone working in academia, we will not be releasing an episode on the 31st. But don't fret, we will be back to our regular schedule in September. Where I want to start is where your book starts, which is not arguing what is the first computer, but with the ENIAC. Can you give me a little background on the ENIAC and why that was the starting point of your new book?
Sure. Well, we did have to start somewhere, and you can potentially go all the way back to the abacus or the invention of counting, and that makes for a different kind of book. We found this worked as a starting point for this particular story because ENIAC is the first computer that combined 2 important characteristics. First, it was electronic. That means it runs orders of magnitude faster than the previous mechanical and electromechanical computing devices. By modern standard, it's very slow, but that's the biggest jump forward in computational speed in all of human history, basically. Usually you have a process of incremental advances, and that jump forward to electronic speed was very important. It was the first electronic computer to be programmable. So that's the other thing we view as a key characteristic of computers. They don't just do one thing, but they can be reconfigured to do a whole bunch of different jobs. What that basically means is they can string together a series of basic arithmetic operations. So you've got division, subtraction, multiplication, addition as the 4 basic operators. And of course, you want to do more complicated things, but you can do all those more complicated things by joining together those basic individual atomic operations.
So is it like a giant calculator almost? Like a basic calculator that you have on your phone? If those are the adding, subtracting, multiplying, dividing?
Well, those characteristics for those operations had been implemented previously in what were called desk calculators. So those would do basically the same thing as the calculator on your phone, at least if you leave it in regular mode and you don't toggle over to get the complicated scientific stuff and all the extra buttons. But they were mechanical things that you might push some buttons, then turn a crank to get the answer.
Okay.
Switching to electronic circuits to represent and manipulate the numbers obviously made the operations go much faster. But if ENIAC had worked like a calculator in that sense and just done one thing when you pushed a button and then waited for you to push another button to do the next operation, the human would be working so much slower than the electronic circuits that there would basically be no point to making the machine that fast. So with the shift to an electronic computer, you also need to shift to a way of having the system perform not just one individual arithmetic operation, but a whole sequence of them. Now, the idea of having the thing automatically perform more than one operation wasn't new in itself. In the years before ENIAC was constructed, and we should, by the way, set the time period for that. So work on it began in 1943, and it had its first trial operation at the end of 1945. After that, it worked for most of the next decade before it was retired.
So it was during the war that they began working on it.
Yes. And there had been some earlier computers, one of which, best known as the Harvard Mark I, had become operational a few years earlier, built by IBM, which was slower. It used electromechanical relays instead of electronic vacuum tubes. And for that scenario, they basically used the same control mechanism as a player piano or a musical box, right? So player piano, you have essentially a roll of paper tape. It's got multiple tracks in it. Each track corresponds with one of the notes that the instrument can play. So the musical tune is encoded as a series of holes in the paper roll. And for those slower machines, it was workable to do essentially the same thing, but with a device that would perform a mathematical operation rather than play a note. So the holes would encode the numbers that needed to be manipulated, but there'd be other codes that represented what the machine should do with the numbers. So that works for encoding a simple sequence of operations. But in mathematics, for example, there might be something the equivalent of what we might think of as a do-while loop in modern programming. Like you have to repeat something a number of times, but then when a certain condition is met, it's time to stop doing that and move on with the next sequence of operations. With those slower computers, you have the roll of tape. If you wanted the machine to do something repeatedly, you would make a literal loop by tying the two ends of the tape together, right? And that's where the term loop comes from in programming.
It was a literal paper loop.
Yep, a literal loop of tape. So you could have a simple sequence, you could have a loop, but when the loop finished, it was the job of the human operator to recognize that, shut the machine down temporarily, figure out what it needed to do next, and continue with it. So the humans were responsible for carrying out what we would think of as branch operations in programming, where the computer needs to decide between several courses of action for what to do next, based on the results that it's got so far, right? Like say if the result was negative, maybe it does one thing. If it was 0, it does another thing. If it's positive, it does a third thing. And they were relying on humans to make those decisions and pick which tape to load into the machine next.
So then there becomes a difference between just an electronic kind of calculator and then a machine that will actually make those decisions?
Yes. And later on, there is a discourse of people trying to distinguish between computers and calculators on that very basis. Because in the 70s, cheap microchip-powered calculators come along. And some of them are somewhat programmable or fully programmable. So people have to start arguing about what's a calculator and what's a computer. But that's really a 1970s discourse. Back in the 40s, the two terms were used pretty much interchangeably. So ENIAC stood for Electronic Numerical Integrator and Computer. But a more powerful machine that followed on built in Britain, EDSAC, the C in that stood for calculator. So people weren't really seeing that computer meant one thing and calculator meant another thing at that time. That's the discourse that comes along later once there are cheap electronic calculators around and there are also electronic computers. So the player piano model worked for the slower mechanical computers, but for ENIAC, it was so much faster that even if it could calculate a whole sequence of things or run through one loop until it reached a termination condition and the computer knew it was ready to do something different, it would still have spent almost all its time waiting for the human operators to set it up to do the next thing. So they realized that to produce a machine that ran at electronic speed, they also needed a way of automating that process of what we would think of as looping and branching, so that the computer itself would handle those operations. ENIAC didn't use the same method of automating those things as later computers. It didn't use program code set up as numbers in its original form of programming when it became operational back in 1945. But we start with it because it's the first computer to combine the electronic speed with the automation of those looping and branching operations that lets it run something that we would recognize as a computer program.
So what was the calculation that was kind of the impetus for creating this machine that needed kind of both the speed and removing that human component?
Well, as you noticed from the dates, the development of the machine was begun during World War II. So it was justified by a single operation. The sponsor of the development effort was the Ballistics Research Laboratory, which was part of the US Army. So at that point, this was a state-of-the-art scientific establishment. It was set up, I believe, between World War I and World War II. And at that point, there was no National Science Foundation, there was no DARPA, there was no Department of Energy. The things we think of as the big government sponsors of science didn't exist. But the government was supporting scientific work in more targeted, more applied areas. And the biggest one of those at that point was in ballistics, serving the needs of the Army. So there was some state-of-the-art science going on at the Ballistics Research Lab in Aberdeen, Maryland. And particularly during the war, a number of very eminent scientists were assisting with the operations there. One of the responsibilities that they had was test firing guns. And obviously during World War II, there was a lot of development of new kinds of guns and ammunition. So the idea was that before the things were sent to Europe to be used in the war, they needed to perform a number of test firings to figure out what trajectory the shell would have. And then they would use the test firings to come up with some numerical constants to feed into an equation. I mean, what the operators know is how far they want the projectile to fly before it comes down again, right? Because they're aiming to explode some people. So they have to know what direction to point the gun in, but they also need to know how far away is the target along that direction. Now, they can't turn a knob to dial down the force of the explosion because that's a fundamental property of the munition that they're using. So the question is, how high up in the air do they need to point the gun for the shell to land where they want it to? And if any of your listeners have played the recently popular game Angry Birds, right, that's basically the same problem that you're trying to solve with the catapult to get the bird to hit the appropriate group of pigs.
I don't play Angry Birds, but when I teach intro physics, inevitably there's a range equation problem in which it's a cannon that's shooting off a cannonball and you have to find the angle or the range. And I always tell students I will never run out of different ways to ask this question. And I think it just goes to show you that's true because we had to develop a computer to calculate all the different ways you can answer that problem.
Yeah. So they need a table that has a whole bunch of different trajectory results for different angles. And then they find the angle that's closest to the distance they want it to go. There also would be correction factors there based on if they're shooting uphill or downhill, according to the wind, according to the temperature. So they would apply a few kind of rule of thumb adjustments there. But the idea is that each of the guns is going to come with this little book of tables chained to it. And they want to have that book when the gun is ready. The problem was producing the guns turned out to be easier than producing the tables. So they had a backlog of work to calculate the tables, which was reaching well into months and meant that they were sending the guns to Europe without the tables that they were supposed to have to use them with. Now, the problem that you mentioned for your students with a cannon, is your cannon being fired in a vacuum?
We assume so, pretty much.
Yes.
That makes it easier, makes a lot easier.
Right. And that's where the thing gets complicated. If World War II had indeed been fought on the moon, then things would have been so much more straightforward in that respect.
Absolutely.
Right. Because everybody in school and in college, they learn how to do calculus. And they learn how to do manipulations and substitutions and moves things around to get a nice, exact symbolic answer. And the problem is, most of the things in the real world, you can't do that for. So calculus teachers can just keep looking until they find problems that the methods they teach the students will work with. But in reality, most problems have to be solved by numerical approximation. And that means essentially, in this case, simulating the trajectory of the shell. So they broke it down into small intervals, I think about 0.02 of a second for each interval. And then just have a handful of things that you need to track. Obviously, you need to track how far has the shell traveled so far horizontally. You need to track the current velocity. Then you adjust the vertical velocity because of gravity, etc. So you do this pretty simple calculation from one instant to the next. But the shell is going to be in flight for a while. So it would take weeks of work for a person potentially just to calculate one of these trajectories. And you need to do that for each of the values on the table. It also gets more complicated for anti-aircraft shells, because in that case, you don't just care where the thing lands. You care about where it is at different points during the trajectory, because you need to set a time fuse to try and hit the plane in the air. So with World War II, there's a particular need for anti-aircraft munitions, and those are even more complicated. So this problem was severe enough that they were able to use it to justify this really quite bold and speculative project of producing an electronic computer on a scale which had not previously been attempted anywhere. And the leaders of the project were at the University of Pennsylvania. John Mauchly had actually trained as a physicist and had had the misfortune to graduate during the Great Depression, when job prospects for physicists weren't great, right? Now, obviously, we all tend to feel job prospects are pretty terrible, like in whatever era we live in. But
right.
I think the Great Depression was particularly dreadful. So he finished up being somewhat underemployed at a teaching-oriented college, and I kind of dabbled around in various ways to try and get a nice research agenda going, but took the opportunity when the government, in preparation for what it understood was going to be the pretty much inevitable entry of America into the war, began to fund the training of people in electronics, which was understood would be a crucial technology during the upcoming war. So that was organized at the University of Pennsylvania. Mauchly went there, retrained in electronics, and then got a faculty position at the Moore School of Electrical Engineering of the University of Pennsylvania. And the other figure that he partnered with early on for the development of what became Eniac was J. Presper Eckert. He, at that point, had earned a master's degree from the Moore School and had been one of their star students, and I think had been enlisted to help run the labs. So with the war coming up, there were government-sponsored contracts for development being issued on a scale that there hadn't been previously. The Moore School was a pretty small school, but it already picked up some contracts, including one for some work on radar. And in 1943, they received the first part of what finished up being more than $500,000 worth of contracts from the US Army to develop ENIAC, explicitly justified again by the need to get these firing tables calculated. The Moore School also had previously, on an ongoing basis, had a contract to calculate the tables employing large numbers of young women. And their job title was computer. So at this point, computer was an occupation of a human, and the name later got transferred to the machines that did the same job. Originally, the machines would have been called automatic computers, kind of like automatic pilots, say. But you can kind of imagine that if we had a situation where no humans were flying planes anymore, eventually we might just use the word pilot to refer to the computer box that flies the plane.
Right.
And that's essentially what happened with computers, because machines turned out to be so much better at doing those routine calculations quickly and accurately that it didn't take long for them to replace humans in that job.
You mentioned that women were employed to run the automatic calculator.
Well, no, the women I'm talking about primarily were just doing the calculations by hand or maybe with a desk calculator.
Oh, got you.
There was an earlier kind of analog-based computer called the differential analyzer, and they had one of those at Penn, which was applied towards the table calculation work. But we're talking about, I think, several hundred women altogether calculating these tables. And the majority of them would have had either just a pencil and paper or a simple mechanical desk calculator to work with.
Was this because it was during the war and just men weren't available? Or it was considered menial work? It does not seem like a time that women would be put in a position where they would be doing something important or useful, unless there weren't men available.
Well, of course, once the war got underway, there weren't men available, right? I mean, everybody knows the heroic poster of Rosie the Riveter. So during the war, women were engaged in manufacturing bombers, building ships, welding, industrial work of a kind that had previously been considered unsuitable for women, and after the war was again considered unsuitable for women and went straight back to being men's work. So one of the things you see with World War II is kind of how arbitrary that strong sex typing of different jobs for different genders turned out to be, and how, despite that evidence that women actually could do all those things, society had no trouble just rolling the clock straight back again afterwards. So the question you're asking basically is is this a Rosie the Riveter type situation, or is it more complicated? And it's somewhat more complicated, right? So we tend to think that before maybe the 1950s, there were no women in STEM, basically, right? That's a kind of the default assumption. And that's truer in some areas than others. There were more women in mathematics than there were in engineering, right? Even before World War II. I think some number in the low double digits of women had earned PhDs in mathematics. Now, of course, you don't need a PhD in mathematics to do these calculations. So the women that they hired to do them, I believe, were all college graduates, but most of them didn't have degrees in mathematics. So they wanted a kind of certain baseline, but you didn't need advanced training in mathematics to do this. You just needed to be kind of reliable, basically, to work consistently, not get bored, follow through. Now, the women were supervised by and trained in part by Adele Goldstein, the wife of Herman Goldstein, who played an important part in the development of Eniac. And she had a master's degree in mathematics.
Okay.
So I think mathematics versus, say, engineering was more open to women during this period. And the more routine, lower status parts of mathematics were more open to women than pure mathematics. So women were concentrated in applied mathematics. And if you think of this kind of very hands-on routine part of applied mathematics, carrying out those laborious computations wasn't done exclusively by women, but it would not be unusual even before the war to have women carrying out those jobs. One of the fields where they needed this routine computation doing was astronomy to calculate orbits.
Mm-hmm.
It wasn't a huge area. There were probably only in the low dozens of people employed doing that kind of work in astronomy all around the world. But I think a significant proportion of the people who were doing that were women. So there was a precedent for having women essentially do the grunt work in applied mathematics.
Okay, that makes sense because the calculators in Los Alamos were women as well. So that was just kind of par for the time.
Yeah, and it's magnified by the war. We know there are women doing those kinds of jobs that women wouldn't usually do. In an area that might usually be a mix of men and women, I think those kinds of work would typically flip to being all women during the war.
And then after the war, when, you have more electronic-based calculations, then did women continue to be part of that process?
Yeah. So there were indeed women involved in operating ENIAC and other electronic machines. And the first 6 who were chosen for that job had all had experience as human computers doing the calculations manually, which makes sense, right? I mean, at that point, no one really knows what skill set you need to work a computer. But you think, well, if they've been doing the calculations manually and know exactly how they're supposed to work and how the numbers behave and change, then they'll be able to see if the computer is working properly and have an understanding of what it's doing and how to set it up.
And be able to make a decision if a decision needs to be made. They have the kind of intuition of what needs to happen next.
Yes. So the Army hired 6, I think, high-performing women from the pool of human computers. They trained them in the use of punch card machinery because ENIAC could only input and output via punch cards, which was a technology that was already decades old at that point. It was widely used for business administration. It had originally been developed for census work. So the numbers are coded onto these little rectangular pieces of cardboard by punching holes in them. So to get input data into Eniac, you punched it onto the cards, and all the information, when it had results, it punched them out on cards, and you then had to pick up that deck of cards and run it through a machine called a tabulator, which would turn the numbers onto the cards into printed output. And then you had the numbers on a piece of paper. The computer could not directly drive a printer or any other kind of output device.
I laugh at the punch cards because nukes don't throw anything away. It just as a matter of rule, I think. In all the labs I've ever worked at, there are always stacks and stacks of punch cards that people have for spare paper. And if you've seen punch cards, they're full of holes. So I don't know why people keep them around to use as scratch paper.
Yeah, I get old library books by Interlibrary Loan, and they sometimes show up with a punch card in the back from when that would have been used at the library desk to check the book in and out. And although the punch card typically has dire warnings on, like not to return the book without the punch card or you pay a fine, I usually feel it's safe just to keep the punch card. So I built up a little collection of them that way, with different university logos on and so on. But yeah, punch cards used to be ubiquitous. I mean, well into the 1970s, the main way of getting data into a computer wasn't to type it on a screen, on a keyboard connected to a screen. It was to punch it onto a card, build up a deck of cards, and then run them into the computer through a card reader.
And then, of course, the horror story is running them to the computer and dropping your box of punch cards.
Yes, yeah, all the people who were around at the time have got stories about that. So ENIAC is run on a trial basis at the University of Pennsylvania, basically through 1946. And then at the end of the year, they start taking it apart, boxing it up, moving it to Aberdeen, Maryland, where the Ballistics Research Lab has been waiting patiently to get it. By the time it's fully up and running again there in 1948, most of the original group of 6 women had already left. But they're remembered for their time as, they've been called the first computer programmers. I find that not necessarily the best name for the work that they were doing, because first it hides that kind of very hands-on, up close with the machine aspect of what they were doing, right? Setting switches and cables to configure it, starting and stopping the computer, taking the punch cards, putting information on them, running them through the machine, running them through tabulators and so on to print it, right? And programmers, based on the later separation of work that happened, are thought of in the 60s as people who kind of sit at a desk with a pencil, writing instructions onto a coding sheet and maybe never actually touch the computer. But it's certainly true that as well as just working ENIAC, because of the expertise that they had, they were also engaged in assisting the scientists and engineers who would come along with a mathematical treatment of their problem, but would have no idea of how do I turn this into this. So to set up ENIAC for a problem, you needed to set a whole bunch of switches on 40 panels that were spread around the edge of a 2,000 square foot room. And you also needed to run networks of wires between the different units. So ENIAC had 20 accumulators which could store and add numbers. It had a multiplier, a divider, a square rooter. It had some more specialized panels. And configuring to solve a problem meant establishing electrical pathways between these different units so that, for example, when a multiplication finished, the multiplier would send out a pulse from a control terminal. And it was your job configuring the machine to make sure that there was a wire running from that control terminal to a bus across to an input terminal on, say, the adding unit that needed to take the results of the multiplication and add that to the number it was already storing. So configuring it to carry out a particular job meant wiring these networks of logical pathways from one unit to another in a way that when one operation finished, the next operation that was needed would be triggered. That was a kind of a complicated and difficult thing to do. Some of the scientists who had problems to solve, welcomed the chance to dive in and really understand how ENIAC worked and did that work themselves. But others relied on the operations team to have the expertise of translating their mathematical needs into a configuration that would make the computer carry out the right sequence of operations for them.
They sound much more like experimentalist in that users come in and say, okay, I want your machine to do this for me. And then as the experimentalist, they set up the experimental apparatus to do that. Today, we'd call them experimental physicists. It sounds more like what they're doing in today's term than just a programmer.
Right. And of course, I think that's a good analogy because ENIAC, as this like one-off custom-built, extremely complicated and unfamiliar machine, is more like a cyclotron than it's like a modern computer. And this is the beginning of the era of big science, right? I mean, this is also when people are starting to construct nuclear reactors and cyclotrons and those big pieces of apparatus. One of the things we talk about in the book, ENIAC in Action, is the description that people would have. So there was just one of these machines available. For several years, it was the only programmable electronic computer in existence. So you have a problem that needs solving. You need to go to Aberdeen, Maryland, like for a couple of weeks, camp out there and get the problem run. And they were using the term expedition for some of these journeys. Coming down from Princeton or from Los Alamos, it does make me think of, say, a 19th century team setting out to a remote place to observe an eclipse or something.
Right.
There's a strong tradition of expeditions in the history of science. And it's interesting to see that that's basically how they're conceptualizing this machine. You have to make the special journey, and then work with the local experts who understand how this particular thing works to get the job done. And then you finish up with results on thousands and thousands of punch cards, and you take those home and like poke them for a while and kind of try and figure out what the machine has told you with the results of running the calculation or simulation. That's
modern day LIGO or CERN. We just call them going away for an experiment, right? We could easily call those expeditions. I think I'm going to start calling my experiments expeditions.
Yeah, bring some class back to things.
Yeah, exactly. So you said that the ENIAC wasn't finished by the end of the war, so it wasn't able to run those ballistic calculations. So what was the first calculation that was performed on the ENIAC once it was up and running?
Yeah. So one of the interesting things about the timescale of getting it ready is there was a period of a year, maybe 18 months, where they were sending in these progress reports and they were constantly saying, we're maybe like 3 months away from having this thing up and running. It's pretty much done. We just need to test it and so on. So they were really very concerned about the prospect of having the job cancelled. But there was already a committee formed at the Ballistics Research Lab to try and think of the jobs that they could run on it. So even within the Ballistics Research Lab, they understood that a machine this flexible and powerful will be able to do a lot more than just those trajectory calculations, which aside from the atmospheric drag, which makes the whole thing a lot more complicated, but it's still conceptually pretty simple. It's just arduous.
Right.
By the time it was ready for its first use at the end of 1945, the urgency had shifted from the production of firing tables. So ENIAC finished up spending about 15% of its time producing firing tables. So it's not the case that it was never used for that, but it wasn't a dominant task in the way it had been in originally justifying it. And John von Neumann had entered the picture on behalf of Los Alamos. So he had learned of ENIAC in 1944. And this had come from a fairly systematic effort he was making to locate computer building projects around the US and emerging technologies that would help Los Alamos in carrying out the large-scale calculations it needed. So at that point, they had a set of electromechanical punch card machines which in the late 30s and 40s were increasingly being applied to scientific problems as well as administrative and actuarial work. But Los Alamos did not, at any point in the 40s, have its own electronic computer. So von Neumann, as one of the few scientists who was a core part of the Los Alamos team, but was also able to come and go at will and move around and visit different groups, was talking to people at Harvard University, at Bell Labs, IBM, about the computer projects that they had in progress. And one day, it's said to have occurred from a chance meeting with Herman Goldstein on the station platform, waiting for a train in Aberdeen, Maryland, after he'd visited the Ballistics Research Lab in connection with a different project, to get talking to Goldstein and learn about the work that was underway at the University of Pennsylvania to build ENIAC. So von Neumann is just famously hardworking and committed simultaneously to a whole bunch of different projects in quite different areas, right? Remarkable for the breadth of his engagement with different areas of science and mathematics. But he immediately appreciated the potential importance of electronic computation for science, visited Eniac under construction, began talking to the members of the team and working with them on the design of an improved follow-up machine. And that story leads to the production of a report called the first draft of a report on the EDVAC, which is the basis pretty much for the architecture of all the computers that have followed.
So what is the EDVAC then? What does it stand for? Does it stand for anything?
EDVAC stands for Electronic Discrete Variable Automatic Computer. So the key characteristic of EDVAC would be that it would have a large electronic memory, able to store thousands of numbers. ENIAC had 18,000 vacuum tubes, and most of those were used to store numbers in electronically. It used, I believe, 36 vacuum tubes to store one decimal digit.
Okay.
Even by the standards of the day, that was a slightly inefficient way of doing it. So what you can imagine there is you've got a computer that is using more than 10,000 tubes to store 200 decimal digits. You don't want to scale that technology up for something that's going to store 100,000 decimal digits. People exaggerate how big ENIAC was, right? People have the impression that early computers filled entire city blocks or that the lights dimmed when you turned them on. And it didn't. It filled like kind of a decent sized apartment, and it used 150 kilowatts of power. But if you tried to scale that up to build something that could store tens of thousands of digits, it really would have been that big.
You say that people exaggerate it, but when you said that ENIAC was 2,000 square feet, I mean, that's the size of probably a decent 3-bedroom or 4-bedroom US house, right? It's as big as someone's house, 2,000 square feet.
Yeah. I mean, it was on one level. So it would be more like one of those newfangled luxury apartments that they build for millionaires, right? That maybe only have 2 bedrooms because you don't buy an apartment if you're a millionaire unless you don't need a lot of bedrooms. But big, giant open plan. The computer went around basically the outside of the walls in that space. So there's actually plenty of empty space on the inside. And when it was installed in the Ballistics Research Lab in Aberdeen, Maryland, it was the only thing on this giant base that had air conditioning. So during the sweltering summers, in some cases, people who were involved with the computer group but didn't specifically work with ENIAC would nevertheless move their desks inside the computer. So there's plenty of spare space on the inside. It wasn't like 2,000 square feet solid packed with circuits. People would be moving around doing their jobs inside the computer space. But yeah, it's big. And the point is, they came up with something that they knew would be reliable enough to work and could be built quickly enough that they could at least plausibly say, you're going to have your tables before the war is over. I mean, it didn't work out. But if they said, we're going to start out with 3 years of really thinking about the best way to do this, and then we'll proceed with the detailed design, it would never have got funded.
Right, because again, they're trying to finish something before the end of the war. So it's time is of the essence.
But von Neumann, in collaboration with the members of the project, had a chance to basically go back to a clean sheet and think about what's a better way to do this. And the crucial thing that they had, something that had been developed by Presper Eckert, the electronic expert on the project team, was an idea for how to produce a memory that could store large numbers of pieces of data using way fewer vacuum tubes than the ENIAC approach. And that was something called the Mercury delay line. So it was inspired by something that had actually been conceived for radar use. So you think of a radar dish, right? It's rotating. So I don't know exactly how fast they go, but maybe like once a minute it rotates all the way around. And you have that screen, you have the little line going around, and you have the pings. And the problem that you have is you want to see the planes and the things that are moving. But the radar is also going to be seeing a whole bunch of buildings and trees and things that aren't moving. So the raw signal is going to be full of pings. And the question is, how do you only see the things that are moving? So the answer was you feed the signals coming in into something that will slow them down so that exactly one revolution later, the signal emerges. Then you logically combine the signal from the last rotation that has just emerged from this tank and the current signal that's receiving from the dish this second, and you only show the pings that weren't there last time round.
So it's slightly delayed.
Yeah. And so that was the idea with the delay line. And there are several ways you could do that technologically, but what they came up with was to have a tank full of mercury and turn the signal pulses into vibrations, I think in audio frequencies, that would move through the tank and come out at the other end after the appropriate delay. Now, Eckert's realization was something that can store, say, 1,000 pulses representing numbers, making their way through the tank at once. If you just take the pulses as they arrive at the far end of the tank, turn them back into electrical impulses, that was what the radar application was doing. But if you then route the output back to the input so that when a pulse exits one end of the tank, the same information is regenerated as input, effectively you have a train of pulses that is constantly looping through the tank. And as long as you can read and write them reliably, you can keep numbers there indefinitely. Now, the problem is if you've got, say, 1,000 digits making their way through the tank, then you might have to wait a while. If the specific information you're interested in receiving just passed through, then you have to wait like an entire cycle for it to come out.
But if you're not tracking a tank, if you're just trying to write something, then waiting a cycle isn't that important.
Right. Yeah. So the computers were designed in different ways to work with this. But the way that von Neumann and the team came up with is essentially, so you've probably heard of the term address in this context, right? Like a computer memory address.
Yes.
And it's one of those things that's a metaphor that you don't even realize is a metaphor. The same way talking about computer memory, right? It's really a brain metaphor. Saying that a computer thinks kind of still sounds controversial, right? But saying a computer has memory, like that just became the word for that thing. So address is basically a metaphor of a street with houses on it. So you've got, say, 100 houses on this street, and each of them can store a 8-digit number. So you give the number of the house that you want, and the computer retrieves the number that lives there. So that's the metaphor of an address. And that's superimposed on the delay line. So the delay line is really working in time. There's no single place in the tank where your number lives. Your number is constantly moving. But the system just has to keep track of what address number is currently being read and keep incrementing that. So you can just ask, fetch me the number from address 54 as a programmer, and then there's some electronics in the system that will figure out what instant that number is going to arrive and wait until it comes out and then give it to you.
That's pretty cool, actually.
Yeah. And at the time, one of the mathematicians at BRL said, maybe this is the wrong metaphor. We should be talking about beats and bars because this is basically temporal. So it's taking a spatial metaphor of addresses and imposing it on a physical system that basically the movement is in time rather than in space because you're waiting for the pulses you're interested in to reach the end of the tank. I talked about this in a paper with my collaborator, Mark Priestley, called The Media of Programming. So that's one of the geekier points. But to pull back from this and the story that we had there, so we've got two levels of digression here. And to come back up and deal with the inner digression first.
Okay, yep.
The availability of this addressable memory that promised that you could store hundreds or thousands of numbers using only a few vacuum tubes meant that you could think about a whole different approach to building the computer. You could make the computer itself much simpler. Instead of having the program spread around all those wires and switches on all those complicated specialized units that were filling this room, you could build a really simple computer that had one arithmetic unit. So Eniac had 20 adding circuits. EDVAC would have only one adding circuit, one multiplier, right? It would have a central arithmetic unit. So the way it works is it's got this large memory. The memory holds all the numbers it's going to be working with. The memory also holds the program instructions. So the programs are just coded as numbers. It goes to the memory, it retrieves a program instruction, it decodes it, it uses that to trigger the control circuits that will make the computer do something. It needs a couple of electronic memory locations called registers to hold the numbers it's currently working on. But it's basically just engaged constantly in fetching numbers from the main memory, doing something with them, writing them back into main memory, fetching the next instruction from memory, decoding it, doing something in a constant cycle. And that promised to let you build a computer that would be much simpler and therefore cheaper than ENIAC, much more flexible and easier to program, because programming now just comes down to writing out the sequence of operations that you want it to carry out, looking up the numerical codes, and then getting those loaded into memory.
So you didn't need a whole team of programmers then?
Well, I mean, you did, right? I mean, there's a lot of programmers out there, but they could be more productive.
Okay.
It also makes it easier, actually, to separate programming and operations work, because the program would be written out as instructions and, say, maybe punched onto a loop of paper tape. Then the job of the operators is to load the paper tape onto the computer. The computer copies all those instructions into memory. Then you read in the data it needs to work on, and then the computer carries out its job. And that's something that's much more recognizable, maybe to someone who used an early personal computer, say in the 1980s, than the ENIAC system with the switches and wires.
So the digression before that was Van Neumann, but I originally asked what was the first calculation on the ENIAC?
So by this point, von Neumann is involved and Los Alamos is involved. So a team shows up from Los Alamos to run some calculations, and the purpose of the calculations was kept secret from the operators. Herman Goldstein and Adele Goldstein worked with the Los Alamos team to translate the needs of their problem into a configuration. One of the operators in a memoir described Goldstein standing in the middle of the room like a conductor, reading out from this big piece of paper how all the switches and wires needed to be set, and them working around the room, setting the thing up appropriately. Now, eventually it seemed like it worked well enough that it produced some results. I think it was March of 1946, they took the results back to Los Alamos. It later became clear that this was part of a huge ongoing effort within Los Alamos to determine the workability of Edward Teller's design for a super bomb, the original attempt at building a hydrogen bomb. And years later, thanks actually to some further calculations carried out on ENIAC as well as by other means, it became apparent that it would just never work.
Right.
But Teller had like enormous force of will and was like attempting to pretty much like bend the universe to hit with his way of doing things. So he claimed that he had been completely vindicated by the calculations and it would definitely work. And the whole thing dragged on for several years after that.
And I mean, eventually he got his bomb.
Yeah, but as you know, the story is that it was only after he finally faced up to reality and admitted that the thing wouldn't work that then with Stanislaw Ulam, they clustered together somehow and came up with the design for the actual workable weapon. I believe the question was the amounts of deuterium and tritium that would be required, right? And one of those was prohibitively expensive to produce.
Yes. And from my understanding, the actual calculation that they ran is still classified.
Yeah, it's actually also not clear. So a little bit later, Eckert and Morkley attempted to patent ENIAC. And under the rules that existed at the time, there's only a window of 1 year from the first demonstration of something working to getting the patent application submitted. And they didn't get their application in until the summer of 1947. So if the machine had worked in December to March when they were carrying out these calculations, then they missed that window and the basic technology of the computer was in the public domain and couldn't be patented. Now, they finished up founding a computer company, which produced what became the UNIVAC, but being bought out by a bigger company, Sperry Rand, and they became the number 2 player in the computer industry after IBM. And they moved very slowly with the process of getting the patent granted. So I believe the patent was only granted well into the 1960s. And it's been said that this was because they realized the potential value of a patent on the basic technology of the digital computer would be growing like larger all the time.
Yeah.
So with appeals and litigation, this question was not finally resolved until the early 1970s, when there was a large federal lawsuit, which finished up with invalidating the patent. But the interesting thing was they were calling witnesses, including the people from Los Alamos, and everyone involved finished up on one side or another of the legal argument. So although it's been suggested from archival research that Teller took the results of the calculations extremely seriously, they got, I believe, Frankel and Nick Metropolis were the, if I recall correctly, the two people who came out. And they gave testimony saying, oh, we didn't take these results seriously. It was just kind of to see, to get a feel for what it was like to use the computer, see if it really worked. And then they had some of the people say, oh, and it turned out later we found a bug in the computer that meant that any results would have been unreliable anyway. And we didn't even find that till later. So really, the computer wasn't ready for use until July of the next year, and therefore it wasn't more than a year, and the patent should be valid. So writing the book, one of the interesting things was because there were legal and patent proceedings running pretty much continually from the 50s to the early 70s, everybody involved with it were keeping all the papers. So there was a huge amount of archival material saved in people's personal collections that then finished up getting donated to different archives around the country. And also depositions and what they were swearing to lawyers and testimony and so on. And there's thousands and thousands of pages of testimony from the trial itself. At that point, it was the longest federal trial in US history in terms of the number of days of proceedings in the courtroom. It also meant that very early on, people were being drilled by lawyers to recall the history in one way or another. And that meant that the narratives get very polarized so early that there's some places where you really don't know what reflects reality.
That's really interesting, especially because so much of that early calculation is involved in weapons research and that information is classified, that there is actually a narrative during that time and not just this black box, which is what so many researchers find when they're trying to write about Los Alamos or Livermore during certain periods.
Yeah. To fast forward slightly with the story, Eniac, as I mentioned, was used at the very end of 45 with those false calculations and through most of 46 at the University of Pennsylvania in Philadelphia. It gets moved to Aberdeen, Maryland early in 1947, and it takes them a while to get the thing working again. So there's a description in Wikipedia that says it became operational again in July and ran continually for the next 10 years or something. And that turns out to be ludicrously untrue. So we went back and we found the log books. It's kind of like the diary of the computer. So every shift they're writing down what it was doing and how it was working.
This is exactly what we do with accelerators. I mean, everything that you are describing, it is a scientific piece of equipment.
Yeah. Years later, Eckert and Morkley were saying, well, it worked fine at Penn. It was very reliable. I don't know what they did to it, over there, but it wasn't our fault.
They moved it.
Yeah, they moved it. They took it apart. I mean, one of the problems they had was they were originally turning it on and off at the end of a shift. And it turned out that with the vacuum tubes, that was when they all failed. So eventually they got around to the idea that they needed to leave it on. I mean, years later, Morkley was saying, oh, what idiots. But what he didn't mention was, towards the end of its time at Penn, it caught fire during the night. One panel was badly damaged. Fortunately, they built in some heat-sensitive switches that stopped the fans once the temperature rose over a certain level that indicated a fire. Otherwise, the ventilator fans would have made sure that the entire computer incinerated. So it wasn't quite so stupid of the Army to be turning it off at night, as they'd suggested.
I was about to feel vindicated for leaving my computer on overnight until you mentioned the fire.
Well, fortunately, I think now there's government standards and things. It's not this one-off 150 kilowatt consuming hand-built monster.
Okay.
We found in the logbook early in 1948, after it theoretically had been working since July, there was a statistician called Frank Grubbs. I think this is pretty much the best thing that can happen to you as a statistician, right? He has a test that has his name on that people actually use. So it's like Grubbs' test, and it's a measure of outliers, right? So you basically want to know statistically, if you've got a number that is like way outside your other data points, is it just, okay, a distribution every 1,000 points is going to give you one of those? Or is it this thing is so far out, it must be that like the machine broke or something, right? That this is probably wrong. So you want a measure of like, how likely is it this outlier is a genuine piece of data or not?
Okay.
And he had been working on his PhD when the war started, and instead of finishing his PhD, went to the Ballistics research lab, found ways of applying statistics to various things the army was interested in, like managing its munition stockpiles. He's got 3 weeks of time on Eniac to help crunch the numbers and build this table that he was working on for this problem of statistically detecting outliers. And it became part of his PhD thesis. So on the one hand, you think, wow, that's a lucky graduate student. But it took almost the entire 3 weeks to get any useful results out, right? So they were coming in kind of tinkering and trying to upgrade the equipment while he was working on it. Then it was just refusing to work. Then it kind of worked a bit, but he discovered he had a problem with his program that meant that the results were no good. The numerical analysis method he was using was not well adapted. So then they kind of fixed that. Then they, a couple of weeks and they finally get some results. They're really excited. Then, of course, under the circumstances, what they have to do is then run it with the same input and see, does it give the same results? And you run the two sets of punch cards through a machine that compares them, and unfortunately, they're different. So one of those sets of results is bad. And then finally, at the end of it, it's working well enough that he gets some results out of the thing. So that is how far away the truth is from Wikipedia's claim that in July 47, it was turned on and it worked constantly 24/7 for the rest of its 10 years there. I don't even know where that comes from.
I think that explains why it's so confusing to read the history of computers. Big mistakes like that are just all over the internet. Another big one is the MANIAC, which there are places on the internet and in physics memoirs that note that von Neumann's EDVAC machine was called the MANIAC, but in fact, that is not true. Could you explain maybe where that confusion comes from?
Sure. So I'll talk through that, and then I'll get back to the progress that they were having in 1948. We'd got as far as talking about the first draft of a report on the EDVAC, right, where von Neumann, drawing on the work that he was doing with the Eniac team at Penn, had come up with this basic design for a modern computer, something built around a large addressable electronic memory that would hold programs as well as data. So von Neumann had described this basic idea for a new style computer built around a large addressable electronic memory. And with the end of the war, I guess he returned to his position at the Institute for Advanced Studies in Princeton, the IAS. But he wanted to continue his work there on designing and building a computer, which was a bit of a change of pace for the Institute for Advanced Studies, which was much more about, conceptual work and thinking great thoughts and talking about things over cups of tea and walking in the woods. So the idea of an engineering group there actually building something was something of a departure, and it was quite controversial. However, von Neumann's group there, which included Hermann Goldstein and Arthur Burks, another veteran of the Eniac project, quickly produced a series of extremely influential reports that extended and refined the ideas from the EDVAC report. And in conjunction with a summer school held at the University of Pennsylvania, were very successful in spreading these new ideas about computing. So groups around the United States, in Britain, in Australia, in the Soviet Union, all started to work along these lines to try and produce computers on that new EDVAC kind of model. Most of the early American computers were specifically inspired by the refinements that von Neumann's team had made to that basic design for the Institute for Advanced Studies computer. And one of those was the first programmable electronic computer that was built at Los Alamos. So Nick Metropolis, who had worked on ENIAC, was the leading force behind that computer. Now, the confusion that you're mentioning is around the name MANIAC. So years later, when people were first working on the history of computing in the 70s, Metropolis was one of the forces behind convening a conference at Los Alamos that was the first conference devoted to the history of computing. And he also produced one of the earliest publications in the area called A Trilogy on Errors in the History of Computing. He was kind of nitpicking, and he was picking 3 nits, which is where the trilogy comes from. But one of those was the idea that MANIAC was the name of the Institute for Advanced Studies computer. And Metropolis, in his article, is very clear. He says, no, it was never called that. A MANIAC, which is a name that's parodying ENIAC and EDVAC and EDSAC and SEAC and all those like something AC machines. And he's just saying, okay, we'll call this one MANIAC. That's going to like make people start thinking of more imaginative ways to name the things. So MANIAC was the official name of the Los Alamos computer based on von Neumann's Institute for Advanced Studies design. But it's still a puzzling question to me, right? If Metropolis is right, and that was never the name of the Institute for Advanced Studies computer, why people keep calling the Institute for Advanced Studies computer that? And for example, George Dyson did that in his book Turing's Cathedral, which despite its name is mostly about the Institute for Advanced Studies computer and von Neumann. And my best guess is that maybe at some point von Neumann or one of the team at the Institute for Advanced Studies came up with this joke, or maybe used it like internally as a name, but that given the controversial nature of a project to actually build something within the Institute for Advanced Studies culture, might have thought that officially calling their computer MANIAC was just, giving ammunition to people who would prefer to not have this banging and clattering and soldering and experimental work going on in their, elite center of quiet contemplation. So maybe it was a joke at some point with regards to the IAS computer that then Metropolis took as the official name for the Los Alamos machine that was based on it.
That makes sense why so many scientists think, and most of the confusion comes from memoirs, I think, that we read. And your explanation makes sense in that regard. And also that it was something that actually happened at the time because Metropolis actually used that as one of his nits to pick. So it was something that was happening. And it's not just looking back, somehow we've made that confusion. It was going on at the time.
Yeah.
He seemed kind of annoyed by it.
Yes. I think partly because it was producing this kind of confusion that people would think, so MANIAC at Los Alamos, did they move the Institute for Advanced Studies computer? It would make it just more complicated to understand what was actually going on.
And I actually read on one website about the history of computing that von Neumann's MANIAC was moved to Los Alamos.
Yeah.
Which obviously it wasn't.
Although all these groups were inspired particularly by the Institute for Advanced Studies computer design, right? Now, by the way, the very fact that I have to use this clunky phrase, the Institute for Advanced Studies computer, when every other machine built in the 40s has got some kind of snappy, like 4, 5, 6 letter abbreviation that ends in AC, it's kind of suspicious in itself, right? It makes you think maybe it really did have that name at one point, because like it doesn't seem to have any name, right? There's no other computer that's just known as the like whatever institute for something or other computer. They all had names except this one.
That does seem odd. What did people call it then? Like von Neumann's computer, John's computer?
Yeah.
Seems like it should have had a name.
Yeah, there actually was a computer at the Rand Corporation called the Eniac.
I actually like that. But again, it was an AC.
Yeah, they were all ACs. Many groups set out to try and build these computers, but the crucial thing was the large addressable electronic memory. But delay line storage and the other method that people came up with, which was using cathode ray tubes, kind of similar to television tubes or oscilloscope tubes, but to use them to store numbers. The engineering was hard because to be useful, these things had to be incredibly reliable. Right, the numbers that were circulating in the delay line had to be read with 100% reliability and written back and stay there stable for hours without any of the bits getting corrupted. Otherwise, the thing is useless. And engineering that proved to be very difficult. So pretty much all the early computer projects slipped on the timeline, and not just a little bit. Something that they thought would take a year and a half finished up taking 5 years to work reliably.
Oh, wow.
So even though this new approach is already extremely compelling to a number of groups by 1946, In 1948, picking up just back with Eniac, just after what I described with Grubbs and his statistical problems that groups at Los Alamos or the Institute for Advanced Studies had started coding on the assumption that their computers would soon be ready, were just sitting there waiting for the engineers to make the memory work reliably. And recognizing this, a little earlier in 1947, von Neumann and a team at the Institute for Advanced Studies and another group at the University of Pennsylvania, headed by Gene Bartik, one of the original Eniac operators, had all been put to work on the idea of we can use the flexibility of Eniac, setting those switches, wiring those electrical pathways to essentially rebuild it into a different computer for each problem that it needs to solve. Now, why don't we find a way to wire it up so that it works like one of these new style EDVAC computers and reads a program that is set up as a series of numerical codes? And it just so happened that ENIAC had a couple of thousand digital number switches, right? It was amazingly well equipped because they were thinking, okay, this thing might be useful for one problem. Let's build that unit. Oh, and here's another one. I'm sure we'll find a use for this. So it got all these specialized pieces of hardware. These switches were originally intended just to hold numerical constants and lookup tables. But then they had the realization, oh, if we code it right, then we can express our program in terms of a series of numbers that represent the arithmetic operations, the branches, the loops, the other things that need to happen. And we can enter the program itself on these same switch panels. So we can essentially have ENIAC emulate the behavior of one of these modern EDVAC style computers. There were some limitations on it. It still only had those 200 decimal digits of writable electronic storage. And because some of those were tied up in the emulation itself, maybe only 150 of those were actually usable by programs. But the advantage was you could write much more complex programs because you had thousands of digits of space on these switch panels. So I'm not going to get into the factors that limited the complexity of a program in the original programming mode. They're kind of hard to get your head around, but you could run out of terminals of a certain kind. You could run out of capacity on the master programmer for doing loops. You could run out of branches. Those were all interacting with each other in complicated ways. So in 1947, there was the new idea of a Monte Carlo simulation, which had come up at Los Alamos in terms of how to model what was going on in a fission warhead as it began to have a chain reaction. There's obviously a very short time period before the thing explodes itself. And during that time period, you want as much fission to happen in terms of the enriched uranium atoms breaking into pieces and releasing energy. And that's the whole question of yield. I mean, they know from Trinity and the bombs they dropped on Japan that the approach they're taking basically works. But they also know that the early weapons are extremely inefficient, right? Particularly the Hiroshima bomb. I believe that only fissioned a few % of the enriched uranium atoms that were in the warhead. So they're all about how can we tweak the weapon designs to get the most effective use possible out of the enormously expensive and slow to produce enriched uranium and plutonium that we have available. And that's the original application of Monte Carlo simulation.
What's interesting here is that we still have Monte Carlo groups at national labs, and Monte Carlo simulations is something that I know a lot of nuclear physicists that apply these to other applications and not just weapons work. So these simulations are still active in multiple areas of research.
Yeah. So I think the basic idea is sufficiently generic that I believe, you can't really talk about the Monte Carlo method. It's more like whole, diverse family of different statistical simulation-based approaches.
Right.
The basic idea is, if you think about something like Brownian motion, right? It's the result of millions and millions of little particles all floating around doing their own things. But scientists were able to find ways to describe it mathematically that you don't have to approach it at the level of simulating individual particles, right? Einstein had some kind of tour de force thing. He wrote down some equations, right? It's a classic thing of like someone standing at the blackboard, like writing down really complicated equations. And at the end, everything cancels out and you just finish with a few terms. And there are areas of physics where people were able to do that, but no one was able to do that in terms of how a chain reaction is going to progress given certain parameters about how enriched the uranium is and the nuclear cross sections and the design of the weapon, and is there a layer that's going to reflect things back, and like how big the different layers of the warhead are, right? You had probably the smartest people in the world, best able to try and do that at Los Alamos, and they couldn't. So instead, the idea is it's fairly simple to see if we look at one neutron inside the warhead and we trace it for a small time period, what's the probability that it collides with an unstable nucleus and causes a fission? What's the probability that it's like absorbed and stops moving? What's the probability that it flies out of the weapon completely? What's the probability that it hits the reflective thing on the outside and gets reflected back in? There's a fairly small number of things that they felt they understood well and could give a good simulation in terms of an individual neutron. And the realization was if we follow 100 neutrons through a sufficiently large number of time cycles, we'll have a pretty good idea of what's going on. And then we just scale that up to say this is a statistically valid sample of the much larger numbers of neutrons that are going to be flying around inside the thing. And we can get an estimate of how much energy is going to be released before the thing explodes itself. So that was the basic idea with the simulation, that you can't do that wonderful symbolic mathematical thing of elegantly solving it. But with the power of the computer, you can just kind of analogous with what they had to do with following the trajectory of the shells in the original Eniac application, but in a much more complicated scenario, follow through from instant to instant the behavior of these neutrons. Now, von Neumann was coming up with a plan for how to do this in 1947. And this is preserved in the declassified Los Alamos materials. And he says in that it could be done on ENIAC, maybe it could be done with punch cards or manually. But it's that application and the knowledge that the Institute for Advanced Studies Computer and the other modern machines won't be ready for some years that gives them the impetus to think about how can we reconfigure ENIAC so it can run these kinds of more complicated modern style programs within limitations. And we don't have to wait for the new computers to be ready. So in March and April 1948, they have the Monte Carlo code written, planned out how they need to reconfigure ENIAC so it can run that code. And a group including Nick Metropolis from Los Alamos and Clara von Neumann, John von Neumann's wife, who had done the computer coding, arrive for an expedition in Aberdeen, Maryland. They're camping out for several weeks with ENIAC. In the beginning period of that, they're reconfiguring it and making sure that the new control mechanism works. Then they start doing the simulations. If I remember right, on that first expedition, they are able to simulate maybe 5 or 6 different weapon configurations, and they finish up with hundreds of thousands of punch cards. Because the thing is, ENIAC has got such a tiny memory, it basically can only simulate one neutron at a time. So it reads in a card, right? The card can hold 80 decimal digits. So they have to code everything about the neutron, like what zone of the weapon is it in, how fast is it moving. They have a very simple one-dimensional model of the physics. So the only thing they know is how far from the center is it, and they're assuming that the weapon is a series of like concentric spheres. So there's certainly a lot of constraints that they have to make to get the simulation doable on ENIAC. So they compress everything that they need to store about the neutron down to those 80 digits, read it in. ENIAC kind of crunches for a while, follows through the branches and loops to simulate what happens to it. Then at the end of a time period, it updates the information on where the neutron is now, what's happened to it in between, and writes out a new card. Then they repeat that for the population of 100 neutrons. I believe they had a procedure where if too many of them had been absorbed or flown out and weren't active anymore, they might need to generate a few more to like make sure they still have a statistically valid sample. So there's a lot of human processing between these cycles. It's not just that they take the output deck and feed it back in again. There's all these manual operations. Then they get it ready, they feed it back in, they simulate another time interval. They keep doing that. And after a couple of days, they've completed one simulation. So it takes weeks to carry out a set of 6 simulations. And in between, they kind of tweak the configurations for different weapons configurations that Los Alamos is interested in. And I mean, then as now, obviously, this might sound arduous, but compared to the amount of work that's necessary to enrich the fissile material and conduct the test, it's like infinitely cheaper and easier, even with that amount of manual work involved with the simulation, to try and run it on the computer first.
Yeah, it would take them 2 years just to prepare for a test. So yeah, a couple of weeks running simulations is a time saver.
And one of the advantages of this is because Eniac has so little capacity inside and is constantly writing out these intermediate cards to represent the position of each neutron after each time interval. They finish up with this enormous stack of cards that essentially they can replay the entire simulation in. It doesn't just give them a result at the end, and they can take that back to Los Alamos, use their conventional punch card machinery to tabulate them in different ways and see exactly how the simulated chain reaction is going through the entire progress of the simulation. So I think if we trace forward in time from those original Monte Carlo calculations that took place in the spring of 1948, we can see several pieces of legacy that has for the later development of computing. So one of those is, of course, the Monte Carlo simulation. Clara von Neumann had the job of being the coder. That is, John von Neumann, her husband, Nick Metropolis, and others produced these detailed flow diagrams of what the program needed to do. The job of the coder was to take that and translate it into those numerical instructions. And although she had no training in mathematics beyond high school, she found that work interesting and engaging. Finished up being involved in several further expeditions for what became Argonne National Lab and Los Alamos for nuclear Monte Carlo simulations with ENIAC. And we did find in the archives some letters later on with members of the Los Alamos team when they finally get their own computer in there, reworking the codes that she developed there. They were asking her for her advice on how to go about developing them. So there's an indication there that the codes later on at Los Alamos are the kind of infinitely evolved but direct linear descendants of this first ENIAC Monte Carlo code produced by Clara von Neumann.
That's actually pretty cool that nuclear physics at that time definitely did not have a lot of women involved. I mean, there are a few, but that this Monte Carlo simulation is based on her original chart.
I mean, the husband and wife model is something that I believe was involved with some of the Los Alamos people. I'd have to check the names in the books. So in some ways, the sexism that's in the area that would prevent women from having their own careers also did give opportunities for these husband and wife teams to have that kind of collaboration, right? And of course, in later generations, the women would be freer to have the careers in their own right. But it seems to be in some ways a surprisingly common pattern for science in this period. Then another one of the threads is ENIAC, after its conversion to use this modern style of programming where the programs are coded numerically in those knobs on the function table that were originally intended to store numerical constants, never gets switched back again.
So it always runs in this kind of like new EDVAC sort of mode.
Yes. They make refinements along the way and kind of tweak the instruction set that's being simulated and so on. But for the rest of its life, up till 1955, it's always programmed in that method. And because ENIAC was already there and just needed to be reconfigured, this is the first time that modern style code is run on any computer anywhere in the world. So there's been a lot of interest in the history of computing in firsts and arguing about like what's the first this and who invented that and so on. And I don't even kind of want to get into all that because there's been argument about like what's a stored program computer and what counts and what's the first one. So the first EDVAC style computer that's designed from scratch and has that large writable memory that's operational is at the University of Manchester in England, and that's in June 1948. So a few months earlier, Eniac, but with the program stored on this write-only switch panel rather than in a delay line or one of the new style memories, runs the new style program. And it's a surprisingly complicated program. It's got more than 800 instructions in it. Often when people look at these first programs, like I think the first program run at Manchester that they're very, very proud of, and is a genuine historical first. I've been involved in helping them get a blue plaque put up on the wall in the lab where it was as a historical marker. So they absolutely deserve their historical recognition. But if I remember right, the program in question calculated a table of squares. And this Monte Carlo simulation is extremely complex. In fact, the flow diagram was much too big for us to reproduce in our book, Eniac in Action. So instead, I printed out posters and I said, I will mail free of cost a poster in a tube with this original flow diagram so you can see the complexity of the thing. To the first 100 people who are interested, there are still a few left, if any of your readers want to jump in. But I've had requests for them, among other places, from the Monte Carlo team at Los Alamos, which said they wanted a couple of posters to put up in their lunchroom, and from the equivalent group in France. So it's been kind of interesting to me that the people who now are maintaining the very distant descendants of this code for a living are seeing enough resonance in it that they still want to have the poster up on the wall.
Yeah. And I can put the website in the show notes because you have a really nice website that goes along with the Eniac in Action where you can see this diagram and the notes from Clara von Neumann and what is on this poster, except in, small computer screen.
Yes. So that's got the detailed story. Now, if any of your listeners are interested in the bigger picture evolution of the computer, then my new book with Paul Ceruzzi called A New History of Modern Computing, which comes out in September. Everything we've talked about now is half of the first chapter of that book. And it continues into the 50s, 60s, 70s, 80s, right? It comes all the way through the pandemic.
So very timely.
Starts with ENIAC. It finishes up with the pandemic and actually a Tesla, which is an illustration of how computers have evolved to the point that most of the computers around us, we don't even think of as being computers anymore. They're hidden away. They're our phones, or they're hidden in our televisions, or there's, 100 computers in your car, right? You go from the ENIAC, where for several years there's only one programmable electronic computer in the world, to the situation now where there are far, far, far more computers in the world than there are people. So readers who would like to know what happens with the story after 1948 will find our attempt to squeeze all that into one liftable volume in the New History of Modern Computing.
And it is interesting. All your favorite characters come to play, including, NASA and the space race, and the Cold War comes in. And I mean, that's as far as I've made it.
And of course, Los Alamos and other nuclear institutions remain important for decades after this in driving the history of computing, particularly high-performance scientific computing. So we've said a lot today, but if you would like to have me back to talk about those later developments through the IBM computers, supercomputers, Crays, and so on, then I'd be very happy to.
That would be fantastic. We'll do a second episode later on. Thank you for listening to another episode of My Nuclear Life, and thank you to Thomas Haigh for answering my ENIAC questions and clearing up some misunderstandings I had about the history of computing, especially the MANIAC naming. To learn more about our podcast and send us an email, head over to our website, mynuclearlife.com. It is here I would like to send out a special thanks to our Patreons whose generous support keeps our webpage up and running. To be included in this exclusive list of people, head over to patreon.com, where we post extended conversations with our guests, which might just fill the void left when we take our little break. We also send them exclusive merchandise. An easy way to support us is to leave us a review wherever you listen to this podcast and tell a friend to listen to. Until September, I'm Shelly Lesher, and this has been My Nuclear Life.